this video, it'll be a brief introduction to how quantum mechanics was first developed. We're going to introduce the history and how it came about, and discuss the three models that were proposed. We currently have evolved beyond all of these models, and we're going to go into that in later parts of the chapter in the course. But right now, it's good to see where that topic originally came from. We'll also go much further into our introduction on waves and electromagnetic radiation, and the relationship between energy, frequency, and wavelength. So you can see that this has quite a list of objectives, but we'll get through them all. Let's go first a bit into the history. Before the era of Max Planck and the resulting studies of quantum mechanics, scientists treated atoms and molecules as simple rebounding balls. There were a few different theories about the actual structures of the molecules that we're going to discuss in a moment, but for the most part, the calculations and the theories were built as treating them as these simple rebounding balls. We'll see that we can use this approximation even now for a lot of different applications, such as when looking at gases under certain conditions. We'll come across all of that later on in the course. The treatment of molecules as these simple rebounding balls works well in describing macroscopic properties, but it fails to explain many of the other interesting phenomena that were really quickly becoming an integral part of science. Max Planck identified that atoms and molecules only emitted very particular wavelengths. In other words, that light coming from the atom could be of several select energies, but never in between these select energies. This meant that energy wasn't continuous, and what seems very simple actually changed everything that we knew about physics and chemistry in terms of this electromagnetic radiation. Now, let's talk about three of the proposed atomic models. The plum pudding model was suggested before the discovery of a nucleus, and it was thought that perhaps the whole atom could be made of this positively charged jelly-like substance, and that there were suspended electrons inside of it. This stopped aligning with experimental data pretty quick, though, and Rutherford used experimental evidence to develop a new model, and what we would eventually call a nucleus. It was at the time, described as a small area of positive charge. Bohr took Rutherford's model and developed it even further. Because of the discovery of quantization, he was able to also say that instead of having the electrons just be surrounding the nuclei, that they were in, you could say, orbits around the nuclei. The Bohr model actually still works very well for a few systems, and we're going to use it for a large portion of this particular chapter. You may also recognize this as the model that they maybe teach in introductory classes in either middle or even into some high schools. However, with more than one electron, it doesn't work as an accurate model. And so we can't really use it for calculations, and it doesn't describe complex bonding very well either. So we're going to be moving on to the more complex quantum mechanic version of these structures. Now, let's go back a bit to Planck. Planck's description of quantum theory also helped to correctly model blackbody radiation. Blackbody radiation describes how light is emitted from an object when that object is heated, and it's temperature dependent. An object at room temperature doesn't appear to have any radiation to us because what it's emitting is in the IR region, and we can't see it, and it's low enough that we can't feel it either. However, as you increase temperature, you increase the energy, and you start to be able to perceive it in some way. First as heat, and then even as some red colors. The wavelength of this energy that is being emitted is dependent on its temperature. And they knew this previous to Planck. But whenever they tried to model it and they tried to use mathematics to describe it, they had completely fallen apart at either the high end or the low end of the spectrum. So they could describe this middle region, but not either area. When Planck realized that molecules could only emit at specified wavelengths, they were able to take this information and apply it to the structures of the molecules to be able to describe blackbody radiation completely. And this was a really, really big deal, and it still is. Now, let's think about this concept of quantization one more time. This is saying that electrons can be at particular energy levels, but not in between. And this can seem a little strange at first. If you think about it, we can be on level 1 and level 2, but we have to move from level 1 to level 2 by using stairs or an elevator. This isn't true of electrons. They're never in between, just one or the other. Now, let's talk a bit more about the blackbody radiation. Our solids emit light. This light is called blackbody radiation. Sometimes you can see this light if the light is in the visible region. For example, when an electric stove is heated, it becomes red when it's at its hottest. You can feel the heat first, and that's the IR radiation. And then as you heat it more and more and more, it becomes a higher and higher energy, and eventually it starts glowing red because it hits the energy level that we can see as red. Space heaters are a very similar manner to this. This is also how incandescent light bulbs, so the old energy inefficient light bulbs, work. A filament on the inside is heated to a very high temperature, and it's kept in an inert atmosphere so it doesn't burn away, and it creates light that we can see. And it's hot enough that it's in the complete visible region, and so we get all of the colors, and we see all of the colors as white. Now, remember what I mentioned about an object at room temperature? It still has blackbody radiation even though we can't see or feel it. So that's an issue of our perception as opposed to an issue of not having blackbody radiation. We can tell by looking at an electric stove versus a light bulb that something is going to be different between the two. So what is it? Well, these blackbody radiators have different temperatures, and therefore they emit very different amounts of light. Take a second and look at the graph here. You may even want to pause, look at the axes, look at the labels, and take it all in before I start to describe it. Now, this graph is what we call a distribution. It might be the first time that you've seen a distribution in this class, but it's definitely not the first time you've seen distributions. Think of it like a grade distribution. A grade distribution tells you how many people in the class got A's, B's, C's, D's, and F's. The same thing here. The line tells you how many photons or what percentage of photons have each particular wavelength. Now, this graph shows a distribution of these wavelengths versus intensity. So you can think of the intensity as a count. The higher the intensity of the wavelength, the more the photons will be emitted at that particular wavelength. Each curve represents a different temperature. Notice at the low temperature, so look at the 3000 K, we're in the infrared region. It just barely stretches into the visible region. We can't see the infrared region with our eyes. If we look at something that has this temperature, we're either not going to be able to see it, or if it was a little bit higher, we might be able to feel it. Now, as the temperature increases to 4,000 and 5,000, so look at those points on the graph, the 4,000 and the 5,000. Now there are lots of photons that are in the red areas, and even some that are in the higher energy blues and greens. So those we might be able to see. And they're going to have the spectrum of the visible, the whole spectrum of the visible in there. Now, as we move up to 6,000, the peak, this represents where we'll have the most photons in the visible region. So any of these times where we're able to have photons of each of the different colors in the visible region will have some form of a whitish color because our eyes perceive all the colors as being white. Now, the exact color we'll see will depend a little bit on the temperature and where in the region it actually falls. It also turns out that there's an equation that helps us convert between the wavelength of maximum intensity. So notice I didn't say the wavelength, I said the wavelength of maximum intensity, the wavelength that the most photons have, and temperature. So we can use this equation to determine the temperature of the object if we have the maximum wavelength or a way of finding it, by simply filling into T lambda max is equal to 2.9 Kelvin, and this is a little odd, but millimeters. So that's how the equation is generally written, is in millimeters. Now let's think about some places this comes up that you can pull from daily experience. We see light bulbs as slightly different colors because of the exact temperature that they are. Now, here I'm talking about incandescent light bulbs, so you'll have to think back to when we had more of those in the house. Complex fluorescent bulbs work on a completely different situation, as do LEDs. Now, different sorts of stars are the same situation. They shine different colors because of their temperatures, as well as a few other things. It's a little bit of an oversimplification, but we can use it here. So red dwarfs and red giants are a lower temperature, and therefore we see them as being more red when we look at them through telescopes, as opposed to the white dwarfs and white giants, which are of a much higher temperature and are emitting wavelengths that span the entire visible region, so we perceive it as white. We'll spend some time talking about these interesting things in other videos and in some of your discussions as well. Now, let's do an example using that equation, and that equation is called Wien's law, to calculate the temperature of our neighboring star, Proxima Centauri. This star is our nearest neighbor, and it's about 4.2 light years away. I tell you that the average is 3042 Kelvin. Now you tell me what region of the electromagnetic spectrum the astronomers find the radiation in. Let's be sure to identify everything that we know first so we work on our problem-solving skills. We know the temperature, and we know the relationship between temperature and maximum wavelength. So using these, we can solve for the wavelength and then fill in the temperature. We can calculate this. Now, given the typical way that it's reported, you're going to get the answer in millimeters. So you could solve for millimeters, or you could convert the entire equation to be in nanometers or meters, whichever way you want to do it. In my case, I solved for millimeters first. And then I converted those millimeters into meters so that I can match it to the electromagnetic spectrum. Now, this also allows us to compare it to the picture on the right. So here we can look over and we can see that it's in the infrared region. So we'll say infrared and we're done with the problem. Now let's do another simple example where we're converting between frequency and wavelength. We're going to continue to practice good problem solving techniques. So first we're going to write down everything that we know. We know the speed of light and we know the wavelength. We know the equation that relates the two. From here, we can fill our known into the equation. We need to be careful with the same issues that occurred in some of our earlier examples. We're given the wavelength in nanometers, and so we need to convert it to meters before filling in order to match with the speed of light. If you have forgotten how to do your metric conversions, please make sure you review that material or stop by and ask for some help. So from here, we can calculate our final answer. We can check and make sure that all of our units make sense. And here we're calculating for energy, and we end up with joules, and so our units make sense. We have 3 significant figures to start with. All we did was multiply and divide by things with 3 significant figures, so we can leave it with 3 significant figures. So now let's review what we covered in this lecture. We covered some historical perspectives of quantum mechanics. We then talked about blackbody radiation, where it came from, and the equation that related it. And finally, we did one new example where we related E to wavelength. We'll also want to spend some time doing some practice on converting between frequency, wavelength, and energy very fluidly. So that's why I stuck in one more example here, and you'll want to do many of those examples because it becomes a much bigger part of larger problems later on throughout the chapter.